Hello, everyone. Today we'll learn about the control objectives in sponge city planning. In sponge city planning, control objectives typically include four types. E. Total runoff volume control. R. Peak runoff flow control. C. Runoff pollution control. C. Rainwater resource utilization, etc. Today, we'll focus on the first three. First, total runoff volume control. The key metric is the annual total runoff volume control rate, calculated based on long-term daily rainfall data. Urban surface runoff can be controlled through enhanced natural infiltration, detention, storage, and purification. This represents the proportion of controlled annual rainfall out of the total annual rainfall. It means the proportion of runoff not discharged externally. The formula is annual total runoff volume control rate equals 100%. Annual external discharge runoff. Total annual rainfall asterisk 100%. Typically, green spaces have an external discharge rate of 15% to 20%. This translates to an annual runoff coefficient of 0.15 to 0.20. Thus, the optimal annual total runoff volume control rate is 80% to 85%. From this chart, we can see that sponge cities and traditional rapid drainage models differ significantly in annual external runoff volume. Under traditional rapid drainage systems, the annual external discharge can exceed 80%. With the concept of sponge city construction, external discharge can be controlled to less than 40% of annual rainfall. The remaining runoff is managed by our measures or naturally retained. The annual runoff control rate can be calculated from daily rainfall data and converted into design rainfall. At least 6 years of data reflecting long-term rainfall patterns and recent climate changes should be selected. Daily rainfall data excludes snowfall and rainfall events less than or equal to 2 millimeters, because 2 millimeters of rainfall does not produce runoff. Rainfall data is sorted from the smallest to the largest daily values, and the total rainfall below a certain threshold is calculated. This involves summing up the actual rainfall amounts below the threshold and calculating the total using the threshold value for any amount above it. This gives the total rainfall below a specific threshold. The ratio of this total to the overall rainfall represents the design rainfall for the annual total runoff volume control rate. The relationship between Shanghai's annual total runoff volume control rate and design rainfall is shown in the table. When the control rate is 75%, the corresponding design rainfall is 22.2 millimeters. In practice, determining the annual total runoff volume control rate requires considering multiple factors. On one hand, pre-development runoff is influenced by surface type, soil properties, topography, and vegetation cover, which should be determined through comprehensive analysis and set an appropriate control rate accordingly. On the other hand, local water resources, rainfall patterns, development intensity, efficiency of low-impact development facilities, and economic development levels must also be considered. For specific plots or projects, factors like building density, green space ratio, and land use layout should also be taken into account. China has vast territory with diverse climatic characteristics, geological conditions, and economic situations, leading to varying total runoff control targets. In western arid and semi-arid regions with high demand for rainwater utilization, and areas with special drainage and flood control requirements, based on economic conditions, the total runoff control target can be appropriately increased. For some coastal areas like Guangxi, Guangdong, and Hainan, where frequent extreme storms lead to significant deviations in design rainfall statistics, reducing investment efficiency and low-impact development facility utilization. And the total runoff control target can be moderately lower, based on statistical analysis of daily rainfall from nearly 200 Chinese cities between 1980 through 2012. The annual total runoff control rates and corresponding design rainfall values for each city were obtained. The mainland China was roughly divided into 5 zones, with minimum and maximum limits for the annual total runoff control rate alpha provided for each zone. These 5 zones are shown in the figure. In Zone 1, the annual total runoff control rate ranges from 85% to 90%. Zone 2 is 80% to 85%. Zone 3 is 80% to 85%. Zone 4 is 70% to 85%. Zone 5 is 60% to 85%. The second control indicator is peak runoff flow control, which is one of the objectives of low-impact development. Low-impact development facilities are affected by storm type and construction and maintenance conditions. Generally, they perform well in reducing peaks for medium and small rainfall events, but have limited peak reduction during major storms, though they still provide some peak shifting and delay effects. To ensure urban safety in low-impact development areas, design parameters such as recurrence intervals and runoff coefficients of urban stormwater pipes and pumping stations should follow the design standard for outdoor sewage systems GB 50014. In local standards, the third control indicator is runoff pollution control. Another objective of low-impact development rainwater systems. It aims to control both the total amount of pollutants in separate systems and the frequency or total amount of pollutants in combined system overflows. Localities should, based on urban water quality requirements and runoff pollution characteristics, determine comprehensive runoff pollution control goals. And pollutant indicators. Pollutant indicators may include suspended solids SS, chemical oxygen demand COD, total nitrogen TN, and total phosphorus TP. That covers the 3 control objectives of sponge city planning discussed in this class.